Good afternoon, everyone. I am Anunitya Parthasarathi.
I am Anakshara Prakashan.
And we are second year BTech students in Metallurgical and Materials Engineering, and it is our honor to serve as your host this evening. A warm welcome to the 35th Professor T. Ramchandran lecture in honor of our founder. We are gathered here today to honor our founder's vision and legacy. Let us begin with the invocation song by our Metallurgical and Materials Engineering BTech students Harshavardhan Gowda and Sripati Anagha Tanmay. May I request you all to rise for the invocation song.
Jaya Ganesha, Jaya Ganesha, Jaya Ganesha, Pahimam. Jaya Ganesha, Jaya Ganesha, Jaya Ganesha, Rakshamam. Jaya Ganesha, Jaya Ganesha, Jaya Ganesha, Pahimam. Jaya Ganesha, Jaya Ganesha, Jaya Ganesha, Rakshamam. Mudakkaratamodakam sada vimukti sadakam kaladharavatam sakam vilasiloka rakshakam anayakaikanayakam vinashiteba daityakam natashubhashunashakam namamitam vinayakam. Jaya Ganesha, Jaya Ganesha, Jaya Ganesha, Pahimam. Jaya Ganesha, Jaya Ganesha, Jaya Ganesha, Rakshamam. Jaya Ganesha, Jaya Ganesha, Jaya Ganesha, Pahimam. Jaya Ganesha, Jaya Ganesha, Jaya Ganesha, Rakshamam.
समस्तलोकशङ्करं निरस्तदैत्यकुञ्जरं दरेतरोदरं वरं वरे भवक्त्रमक्षरं कृपाकरं क्षमाकरं मुधाकरं यशस्करं नमस्कृतां नमस्कृतां नमस्करोमि भास्वरम्.
जय गणेश, जय गणेश, जय गणेश, पाहि मां. जय गणेश, जय गणेश, जय गणेश, रक्ष मां. जय गणेश, जय गणेश, जय गणेश, पाहि मां. जय गणेश, जय गणेश, जय गणेश, रक्ष मां. नितांत कांति दंत कांति मंत कांतिकात्मजम् अचिन्त्य रूपमन्तहीन मन्तराय कृन्तनं हृदान्तरे निरन्तरं वसन्तमेव योगिनां तमेकदन्तमेव तं विचिन्तयामि सन्ततम्. जय गणेश, जय गणेश, जय गणेश, पाहि मां. जय गणेश, जय गणेश, जय गणेश, रक्ष मां. जय गणेश, जय गणेश, जय गणेश, पाहि मां. जय गणेश, जय गणेश, जय गणेश, रक्ष मां.
Thank you very much, Anagha and Harshvardhan, for setting up the stage. To proceed with the program, may I request Professor Kumkum Banerjee, Head of the Department of Metallurgical and Materials Engineering, NITK Surathkal, to kindly escort our esteemed dignitaries, Professor Subhashi Yaragal, Deputy Director, NITK Surathkal, Dr. R. Balamuralikrishnan, Director, Defense Metallurgical Research Laboratory, Hyderabad, to the stage. Please join us on stage.
As a mark of respect, I request our HOD and Dr. Shashibhushan Arya to welcome our Deputy Director with a bouquet of flowers. Now may I request Dr. Lipak Sahu to join our HOD to welcome our Chief Guest and Speaker, Dr. R. Balamuralikrishnan, with a bouquet of flowers. I now request our BTech student Shubhang Kalagali to present a flower bouquet to our HOD.
A very warm welcome to the dignitaries on the stage. We are fortunate to have Mrs. Balamuralikrishnan with us in the audience, and may I request Dr. Suman Govindarajan to welcome Madam with a floral bouquet. May I now request Professor K.N. Prabhu sir to welcome our honorable former HODs with floral bouquets. Now I request our HOD to deliver the welcome address.
Good afternoon, everybody. The situation of my throat is very bad. So you can see that I welcome you all. And I'd like to request my learned colleague, Dr. Suman Govindarajan, to please do the honors for me. Thank you.
So the words are all on HODs. So respected director, deputy director of NITK, and esteemed president of today's function, Professor Subhash Yeragal, renowned speaker of the Professor T. Ramchandran lecture series, Dr. R. Balamuralikrishnan, gracious Miss Balamuralikrishnan, honored colleagues, esteemed guests, and dear students. A very good afternoon to each and every one of you. I extend my warmest New Year greetings for 2026 with and wish you all a happy, healthy, and profoundly fulfilling year ahead. It is my great honor to welcome you to the 35th Professor T. Ramchandran lecture. We are all truly privileged to have Dr. R. Balamuralikrishnan, the eminent director of the Defense Metallurgical Research Laboratory, Hyderabad, deliver today's distinguished address. Our director, Professor B. Ravi, regrets his inability to attend due to prior commitments, and we are most fortunate that our Deputy Director, Professor Subhash C. Yeragal, has kindly consented to preside over this gathering. For the benefit of our students, I would like to briefly recount the genesis of this cherished lecture series. The Professor T. Ramchandran lecture series was inaugurated in 1991 to honor the founder head of our department, Professor T. Ramchandran. He joined the department in 1965 and played a pivotal role in building its infrastructure and research foundation. A dedicated teacher and a mentor, he also served as principal of KREC, now NITK, for 2 years. In recognition of his contributions, he received the Distinguished Alumnus Award from the Department of Metallurgical Engineering, BHU, Varanasi in 1973, and was a visiting scientist at Max Planck Institute for Ferrous Research, Düsseldorf, Germany during 1975 to 1976, 83 to 84, and 1990. Upon his retirement in 1989, his former colleagues and students established a fund to sustain an annual lecture in his honor. Contributions from the National Seminar, MetMat 89, and a generous donation of US dollars 10,000 from alumnus Mr. Nagaprakash Babu in 2013 have kept the series financially self-sustaining. We are profoundly grateful to Dr. V. Ramchandran, former faculty and expert in non-ferrous extractive metallurgy, Arizona, USA, for his tireless efforts in mobilizing additional support. I would like to welcome our Honorable President of today's program, Professor Subhash C. Yeragal, Higher Administrative Grade Professor, Department of Civil Engineering and Deputy Director of NITK, who has very kindly consented to grace this occasion despite his engaging schedule. Welcome to you, sir. On behalf of the Department of Metallurgical and Materials Engineering, I extend a heartfelt welcome to Professor Yeragal and warm and sincere welcome to our chief guest, Dr. R. Balamuralikrishnan and his spouse, Mrs. Balamuralikrishnan, to the 35th lecture in Professor T. Ramchandran lecture series. I heartily welcome my honored colleagues, esteemed guests, and dear students to the lecture. We are truly honored by your presence. I would like to add here that the 35th lecture was originally scheduled for 26th November 2025, but because many undergraduate students would have already departed for winter break and internships, we rescheduled the event to today's date, and when the campus is again active. So I deeply grateful that Dr. Balamuralikrishnan could accommodate us despite his demanding schedule and frequent summons to Delhi. In fact, day before yesterday, he flew to Delhi from Delhi. He came straight to Mangalore, graced the occasion. We are truly honored to have your presence, sir. On a personal note, Dr. Bala and I both conducted postdoctoral research at Carnegie Mellon University while our HOD was there for a brief period. He spent several years completing his degrees. Coincidentally, as he prepared to return to India to join DMRL Hyderabad, our HOD was returning to NML Jamshedpur. His intellectual brilliance has propelled him to the pinnacle of his career. I once again extend a warm welcome to our President, Professor Yeragal, our Chief Guest, Dr. Balamuralikrishnan, all participants, and especially to Mrs. Balamuralikrishnan, whom I am delighted to meet again after 25 years. Our last encounter was in Pittsburgh restaurant with Dr. Bala. So with this, I welcome you all once again. Thank you.
Thank you, ma'am, and thank you, sir, for the welcome address. To mark the beginning of the Professor T. Ramachandran lecture, I request the dignitaries on the stage and off the stage to light the lamp. May I welcome Mrs. Balamuralikrishnan and former HODs to join in lighting the lamp.
Deep
The lamp symbolizes knowledge and wisdom. Let us pray for guidance from the Almighty God. I kindly request Dr. B. Rajashekharan to introduce our chief guest and expert speaker, Dr. R. Balamuralikrishnan.
Good afternoon, everyone. And Professor TR lecture series is our pride and cornerstone of our department. Each year we get this opportunity to invite dignitaries in the field of material science and engineering from India's leading institutions or from leading laboratories. And this year we are very fortunate to have an eminent scientist from DMRL who is currently the director, Dr. Balamuralikrishnan. It's my great pleasure to read his bio sketch here. Dr. Balamuralikrishnan, outstanding scientist and scientist H, is presently the director of DMRL Hyderabad. He obtained his BTech in Metallurgical Engineering from IIT Madras in 1991 and his MS and PhD in Material Science and Engineering from Carnegie Mellon University, Pittsburgh, USA. His research interests include physical metallurgy of high-performance steel, nickel-based superalloy with a strong emphasis on advanced microstructural characterization and establishing the structure property correlations in the important engineering materials. He also interested in applying modeling and simulation tools to study materials and processes. He has first-hand experience of 30 plus years in working with specialty steels across the entire spectrum from concept to product. His work has been influential in establishing the entire ecosystem, starting from lab scale scientific studies to industrial scale production and certification for final use, for manufacturing of specialty of steels for novel constructions. He has a strong interest in fostering interaction between academia, R&D institutions, and the industry sectors towards transitioning concept to the products. He has delivered more than 120 keynote lectures, invited talks at various R&D institutions, academia, industries, and government bodies and conferences. These includes the prestigious Professor E.G. Ramchandran Memorial Lecture in IIT Madras in the year of 2023 and Professor E.C. Subbarao Distinct Lecture in IIT Kanpur in 2024, Professor M.L. Kapoor Lecture in IIT Roorkee in 2024, Professor Brahm Prakash Memorial Lecture in Indian Institute of Metals, Kalpakkam Chapter 2024, Dr. Daya Swarap Memorial Lecture in Indian Institute of Metal in 2025. Besides, Dr. Balamuralikrishnan has received several awards and honors. These include DRDO Agni Award for Excellence in Self-Reliance in the year of 2005, Herbert Haron Fellowship from Indian Institute of Science in the year 2010, DRDO National Science Day Oration Silicon Medal in the year 2011, Metallurgist of the Award by Ministry of Steel in 2017, Outstanding Researcher Steel in an Academic Institute and R&D Labs Award by Indian Steel Association in 2019, and G.D. Birla Award for Excellence in R&D, Indian Institute of Metals in the year of 2025. And I'll invite Dr. Balamuralikrishnan to deliver his talk on From Atoms to Application, Unlocking the Thrilling Power of Material Science, which is a compelling and interesting talk in modern material science. Sir, we invite you to the... Okay. Okay, thank you, sir. We look forward to a talk. So with this, my introduction note about Dr. Balamuralikrishnan, sir. Again, I welcome you, sir, for this wonderful talk. Thank you.
Thank you, sir, for the introduction. Now, may I request our Deputy Director, sir, to kindly say a few words of inspiration to the gathering.
Very good afternoon. I deem this a great pleasure to participate in this inaugural of the 35th Ramchandran series lecture. In fact, I remember last year also I was here, so really delighted to be amongst you. I am honored on behalf of NITK Surathkal to have such a learned personality, Dr. R. Balamuralikrishnan, to be delivering. So I think his resume or the brief sketch presented talks volumes about his contribution to the nation. And it is said, to be conscious that you are ignorant is great step to knowledge. So I think definitely sir has found time to be amongst us, and this lecture is going to be memorial. First, to honor Professor T. Ramchandran. I have been a student here when he was principal for 2 years. Very submissive, very gentle, very nice personality, though I have never talked because I was in civil engineering. But I used to see him moving around with his colleagues. And in fact, it's a great honor to have retired professors whom I know very closely. K.L. Bhatt sir was Dean Administration. I worked with him. Hebbar sir I know very closely. Professor Sudhakar Naik I know. I have an alumnus here. We are just chatting. So indeed, this institute is really blessed to have a lot of alumni people joining back, including me. So I am running now 61. I have spent close to 30 years on this campus, 4 years as a BTech student. So it's a great feeling. It's a great attachment to the institute, and a lot of people have come back, given their best. So I would take this opportunity to appeal to all young friends. Very happy to see so many of you in this hall. I was not expecting. I think it is 100% turnout, maybe because of today's great speaker. So I once again personally and on behalf of Director NITK Surathkal, faculty and all of you would like to very sincerely thank Dr. R. Balamuralikrishnan for sparing his valuable time, and he has come forward to share his expertise today. Thank you so much, sir. It's our honor to have you on campus. So a lot of things probably which he is going to stress should be the starting or the kindling or the invoking or pricking things for youngsters to take forward the ongoing research for nation building first. Definitely, I think we as Indians should help ourselves to lead the world. No other country is going to help us. This is the bottom line message very recently given by our new chairperson, Board of Governors. So we have to help ourselves. So no other country definitely is going to come to our rescue and help. So with that note, please encash what is available. If you ask me, are the facilities sufficient? I have traveled more than 15 countries. So if you ask me anything you do not have on this campus, I would say everything you have at your disposal. You are blessed with opportunities. You are blessed with skills. So it is a great learning place. Please encash everything to your advantage and you have to build your career. So I look forward to a very meaningful discussion, and also I saw the event schedule. A lot of professors are requested to share their experiences. I would personally love to listen to, of course, the origin of Ramchandran lecture series itself talks about the idea of the department's initiative, because this metallurgy and materials engineering was founded by great personality like Professor Ramchandran. I think we have his video also to be played. Okay. With that, I wish the day's proceedings all the best, and I once again take this opportunity to thank the head of the department, the faculty, the retired professors, and the current generation of students for making it to this event. Thank you. May God bless all of us.
Thank you, sir, for your wonderful words. Now I request HOD ma'am to accompany the chief guest and deputy director of the stage and join the audience. Our honorable founder head, Professor T. Ramachandran sir, has sent a message for us. He has very thoughtfully composed the message. I kindly request Professor Jagannathan Nayak to read the message for us.
Namaskar and good evening to all of you. I deem it an honor and privilege to read the message from my most respected, beloved Guru, Professor T. Ramchandran. In fact, he is the Guru of Professor Narayan Prabhu as well. Me and Professor Narayan Prabhu, we attended his physical metallurgy class together, if I remember correctly. Because at those times, our PG students, in addition to their regular courses, they used to attend undergraduate classes also to gain some additional knowledge. Unlike the present PG students who wish to go to other departments for electives rather than studying metallurgy. I'm sorry about that. So that way, me and Professor Prabhu, we were classmates in Professor Ramchandran's class. Anyway, I'm here to read the message from Professor T. Ramchandran, who is 97 years of age right now. And even at this age, he has written such a long message, which only speaks about his love and affection towards the department. So I'm very glad to read his message, and his message goes like this. Professor Subhash Aragal, Dr. Balamuralikrishnan, Professor Banerjee, other distinguished guests on the dais, in the audience, faculty, staff, and students of the Metallurgical and Materials Engineering Department, ladies and gentlemen. It gives me great pleasure to talk to you on this occasion of 35th lecture of the lecture series. I have always maintained that my name in the series is incidental, and I consider myself fortunate to have been the agent for this annual function. The great thing is that this opportunity to invite a distinguished person to interact with the students and staff and expose them to the expert's specialized field. So, we have today Dr. Balamuralikrishnan, an outstanding metallurgist and director of DMRL with us. Apart from these credentials, I have a personal interest in two aspects. His name is a hallowed one in classical Carnatic music, and at least one of my students at IIT Madras, Professor Prabhakar, must have taught him, making him my student's student. On all counts, I express my happiness at his giving this lecture. I thought this would be an opportunity for me to strike a slightly autobiographical note and retrospect on the state of affairs in the 1950s and 60s as far as research in engineering field in our country was concerned. Although details in each individual case may vary, I think my foray into teaching and research was quite typical for those times. The first 5 years of my life after graduating in metallurgy from BHU were spent in preparing for career in foundry field. This included 2 years of supervising work in small foundries in Bombay, a postgraduate course in foundry technology and management in England, 2 years of paid graduate traineeship in a large foundry complex in Scotland. These were the years when the Europe was busy rebuilding after World War II. A lot was happening, and Germany, totally destroyed in the World War, was working at a furious pace, also engaged in India in setting up the Rourkela steel plant. I thought I should round off my foundry training in some experience in Germany. So I wrote from Scotland to several German firms for a trainee appointment. The technical director of one of the firms, a professor, responded positively, and I joined the firm, a reputed malleable iron and special steel foundry, when my Scottish tenure was over. It so happened that this company was a high-tech one with a product mix of high-quality malleable iron castings and high-alloyed steels, covering corrosion and heat-resistant applications. So they had a very active R&D laboratory, and with many students working on their master's thesis and many staff engineers working part-time on their doctorate. After a few months on work training, the professor suggested that I shift to R&D laboratory and work for a doctorate. The professor had an honorary position in the technical universities of Aachen and Gloucester. So, by sheer chance, I changed the direction of my career from that in foundry to research and eventually to teaching and research. The completion of my doctoral work, significant part of which was carried out at Max Planck Institute, Düsseldorf, Germany, on deputation, coincided an advertisement for recruitment of the first group entry-level teaching staff for IIT Madras being started by German collaboration. 20 Indians already in Germany in industry bar academia were to be selected in 2 batches, and these were to spend 2 years in German technical universities to familiarize themselves with the system there before being posted to Madras. The interviews took place in Indian Embassy in Bonn, with the ambassador himself chairing the committee and Professor Krauss, coordinator of the German government, taking an active part. I was the only candidate for metallurgy, and I had my thesis copy with me, so I was selected as assistant professor. As I already had contact with the Technical University of Gloucester, I spent my 2 years at the Institute of Physical Metallurgy and Metal Physics with Professor Wasserman. The engineering colleges in India, like medical ones, were essentially teaching institutions in the colonial times to provide just subordinate support to the rulers. The first attempt to change this happened after independence. But developing a research culture takes a lot of time and effort. For persons of my generation, the task was cut out to initiate research activities. We were not just walking into an existing setup to continue the work what is going on there. We had to create infrastructure and then offer leadership to a new generation. Therein lay the challenge. The present generation has no idea of the struggle we had to wage against bureaucratic obstacles, limited funding, and so on. The main problem still existing, at least in educational field, is ignorance of the special needs of research work and workers. I left IIT Madras for complex reasons after active teaching of 2 graduating batches, was unhappy with the atmosphere there, had an offer of a position in Gloucester, accepted it and resigned. But owing to domestic pressure and the fact that I would have to start a new life with 3 children under the age of 5 in strange surroundings. When I moved out to Surathkal, I got complete freedom to set up a new department. As there was no other metallurgy department in the university, it was possible to plan the curriculum without interference. We were fortunate that right from the beginning, teaching did not suffer for want of staff. We had several master's degree holders from IASC and IIT Kanpur, and a couple of PhD from Canada and US, staying with us for a couple of years while they were preparing for their higher studies bar jobs abroad. They not only taught courses, but also took part in the planning of the laboratories. They were devoted to the profession and retained contact with us even after settling elsewhere. Gradually, more staff members joined for permanent positions. Dr. K.A. Natarajan resigned his post in Trichy as he found the atmosphere in Surathkal was more congenial on a visit and joined us with a project ready for execution. All he wanted was some space, small funding, and encouragement. We gave all that in good measure, and that became the first major successful piece of research in the department. As the quality improvement program kicked in, the young people were deputed for master's and doctoral work. Those on PhD work were advised to prepare research projects based on their work, as there would be loose ends to be tied up. These were submitted to funding agencies, and this is how research progressed in the department over the years and became part of the culture. The same thing was extended to the staff members who are doing PhD in the department. We also kept an open house for others to make use of our facilities. Several young people, for example, from Manipal Dental College, did their master's project work on dental materials with the help of our department. One staff member from Mangalore College did practically his entire PhD work in chemistry during night time in our department. We never made it official, as that would have complicated matters. A small risk was involved, of course. I think the metallurgical engineering department was one of the two which deliberately changed the complexion of an essentially teaching setup to teaching and research. Soon enough, this became an example for other departments to follow suit. I think I have spoken more than I intended. It remains only for me to thank Professor Kumkum Banerjee and the Department of Metallurgical and Materials Engineering for giving me this opportunity to talk to you on this occasion, and to wish the students all the best in their coming examinations and in their career thereafter. I wish the staff members all the best in their endeavors, and those who are on urge of retirement, a happy, active, and healthy retired life. I have to mention the enormous amount of affection I have received over the years from the department, and I used to feel that my visits every year were a pilgrimage for me. Thank you for your patient listening, and wish a good afternoon for useful discourse. That's it.
Thank you very much, sir, for the message. May we now have the video message from Professor T. Ramachandran, sir, to be played for us.
Professor Ravi, Dr. Balamuralikrishnan, Professor Banerjee, other distinguished guests on the dais, in the audience, and staff members and students of the Metallurgical and Materials Engineering Department, ladies and gentlemen. It gives me great pleasure to talk to you on this occasion of the 35th lecture of the lecture series. I have always maintained that my name in the series is incidental, and I consider myself fortunate to have been the agent for this annual function. The great thing is that this opportunity to invite a distinguished person to interact with students and staff and expose them to the expert's specialized field. So we have today Dr. Balamuralikrishnan, an outstanding metallurgist and director of DMRL, with us. Apart from these credentials, I have a personal interest in two aspects. His name is a hallowed one in classical Carnatic music, and at least one of my students at IIT Madras, Professor Prabhakar, must have taught him, making him my student's student. On all counts, I express my great happiness at his giving this lecture. At the time I joined NITK Surathkal, there was lack of clarity about the status of regional engineering colleges. The colleges that were established before independence were essentially teaching institutions set up to do subordinate work for the colonial rulers, all important senior positions being occupied by them. So, as in the then medical colleges too, research was never part of the scheme of things. For persons of my generation, the task was cut out. To initiate research activities, we had first to create infrastructure and then offer leadership to a new generation. We were not just walking into an existing setup to continue the work we were doing. Therein lay the challenge. We were fortunate at Surathkal that right at the beginning, teaching did not suffer for want of staff. 3 or 4 master's degree holders from Indian Institute of Science and IIT Kanpur and 2 PhDs from Canada and the US joined right at the beginning and stayed a couple of years with us while they were planning their future careers. They were highly motivated and enthusiastic young people, and besides teaching courses, helped with the planning of laboratories. There was a busy atmosphere prevailing. Even after settling down elsewhere, they retained contact with the department. Gradually, more staff members joined for permanent stay. The first person to initiate serious research was Dr. K. A. Natarajan, who on a visit to Surathkal found the atmosphere in the department very congenial and moved over from his Tiruchi post. He had a project ready and wanted only some space, modest financial support and encouragement. We gave him all that in good measure. The project was a success. Meanwhile, our staff members used the quality improvement scheme for masters and PhD courses. The PhD aspirants were advised to prepare research projects based on or resulting from their work to be submitted to funding agencies on their return. This worked very well, and that's how research progressed in the department. This was repeated in the case of staff members working for PhD in the department. Slowly but surely, research became part of the departmental culture. We kept an open house for others to make use of our facilities. Several young people from the Manipal Dental College, for example, did master's project work on dental materials in our lab. A college teacher from Mangalore did the major part of his PhD in chemistry in our lab, working at night. I think our department was one of two that deliberately changed the complexion of an essentially teaching setup to teaching and research. Soon enough, this became an example for other departments to follow. I hope you appreciate the context that made me make these elaborate remarks. It remains for me only to express my heartfelt thanks to Professor Kumkum Banerjee and the Department of Materials and Metallurgical Engineering for giving me this opportunity to talk to you on this occasion, and to offer the students the best wishes in the examinations to come and in their future career. My best wishes to the staff members in their endeavors. To those on the verge of retirement, I wish a happy, healthy and active retired life. I thank all of you for your patient listening and wish you a useful and interesting afternoon. Thank you.
After a mesmerizing and rejuvenating message from Professor T. Ramchandran sir, I humbly request our former HOD, Professor Sudhakar Nayak, to share his memorable experience with Professor T. Ramchandran.
Good afternoon. I had the privilege of working with Professor T. Ramchandran. I deliberately said working with, because I could have said I was working under Professor T. Ramchandran. That gentleman professor never treated any one of his junior colleagues as his subordinates. He always used to treat us as his colleagues. Probably your deputy director must have seen how we staff members, faculty members rather, going with Ramchandran for Samudra Darshana, for tea, all of us were going together, chatting like that. There was no barrier between the head of the department and us. This quality of treating junior colleagues is not found in other petty chieftains, right? So that quality is the one to be appreciated in Professor Ramchandran. After his graduation from Banaras Hindu University in 1950, he moved to UK. Well, the same university honored him later as one of the distinguished alumni. That shows how good he was in his studies also. It was the time when there was mining and metallurgy was taught in BHU, not as metallurgy as such. Then, after working for 2 years in foundries, he moved over to West Germany. At that time, unification was not done. It was West Germany. There also he worked in many steel industries and foundry side. And simultaneously he was with Max Planck Institute for Max Planck Institute for Iron and Steel, Düsseldorf. Incidentally, I also happened to go to the same institute while being here. Then he, from his work in the steel industry and some work with Professor Engel in Max Planck Institute, he submitted his thesis to Clausthal University and got his Dr. Ing. And after getting the degree also, he stayed there for 2 more years as a trainee to join IIT Madras later because of German training required, like a teacher training, what we have in our India. So he came back and joined IIT Madras in 1960. So 1950 to 1960, he was 2 years in UK and another 8 years in West Germany. He had learnt German language well in the 10 years. And he used to tell me, when you go there, you must speak German. You may find it difficult because they hate literally English people and English speaking people. So you should learn. Then I said, I don't know German. What is to be done? And then he said, I will teach you a few sentences. With the help of that, you can manage. Something like that. Ich musste eine Tasse Kaffee. I want a cup of coffee. Like that, he taught me certain sentences, and believe me, I managed with that kind of coaching for 1 year in West Germany. Right. Till 65, he was there in IIT Madras, and he came here as professor and head of the department. Hardly 3 or 4 people have joined this college straight away as professor and head. He is one among them. Professor Subbarao, Professor Ramchandran, Professor Ivinaik, and maybe K.R. Kamath may help me in finding out whether Karakareddy also came as professor and head. Yeah, so then it is 4 people. Because I was not sure whether because he was something like that emeritus professor, but he was also heading the department, yes. We all started with our career with assistant lecturer to lecturer, lecturer to assistant professor in those cadre, not like now, and professor. And I could move still further. I became dean and I became the director also. Of course, only 2 people who have raised from assistant lecturer to the director. One is me, another one with my namesake, Professor Sudhakar Shetty. He is also Sudhakar. Right? 2 of us were straight away. He became the principal of KREC and I became director of NITK. It's like that. Then, when he joined here, the department, it was a very small one, not having any facilities at all. It is he who developed the infrastructure and teaching faculty here. Developed in the sense, he himself is a very good teacher and he wanted good teachers. That he is a very good teacher, Jagannath Nayak and Prabhu, you know him. And I will tell you a person who was from the 3rd batch and a professor of metallurgical and materials engineering at IIT Bombay, Dr. N. Bharat Ballad, who is with us. He will watch for that. Because in IIT Bombay also, he said to me that he has adopted the teaching technique of Professor T. Ramchandran. So, it goes without saying that Ramchandran was a very good teacher also. And he was always very particular in selecting good teachers. You know, the faculty members who are present here with him in the initial stages, two names I think Jagaratnayaka has already read, Professor V. Ramchandran and Kadambi Raghunath, and then V. Parameshwaran, Professor T.C.M. Pillai. Oh, I missed the most important name, C.G. Krishnadas Nair. He was the head of HAL, the first civilian to become the CMD, Chairman and Managing Director of the HAL. He was there. Prem Kumar, K.A. Natarajan. Like that, many people, stalwarts were here with the department. Later, youngsters, Sylvia, who did not have any firm footing elsewhere, and a local, most of them being local people, joined here. It was a good exercise to teach in the undergraduate courses and postgraduate courses. Research concept in KREC, because I was speaking the era of the KREC, started only after K.A. Natarajan joined the department. At that time, we had Professor B.H. Kalkareddy, a very senior emeritus professor of electrical engineering in the electrical engineering department. It was undivided electrical engineering. You know, electrical department here split, became E&C, then got further split from computer. I don't know what has become now. Right. The AI can make anything out of that. Professor Natarajan, for Natarajan, Karakareddy used to give, because he was working with Ramchandran, any amount of money, whereas for others, he would say like this, Professor Karakareddy will say no. His hand will be like this, anything that you go and ask, he will say no. Is the principle, because it was a very hard time those years. The grants were very limited, and just it was sufficient to pay the salaries of the people, and the salaries was also not much. You may laugh at it. At the time when I retired as the director of this, my salary was less than 40,000, for your information. So the salary was also very less. Then, because of Professor Ramchandran, we could have interaction with R&D organization, very reputed R&D organization, and esteemed institutions, with the people with them. Let me start with the DMRL itself. We had V.S. Arunachalam coming here quite frequently, then P. Ramarao, Deepankar, Anke Sriramurthy, then Malkondaya, right? Yeah, Malkondaya. Those are the people who have come over here, gave lectures. And Ramarao had come twice. I think V.S. Arunachalam, because he happens to be close friend of Professor T.C.M. Pillai, he made many trips. Deepankar made 1 or 2 trips here. So those are, see, the people who have worked with, Deepankar has worked with J.C. Williams, right? So like that, those are the great people who have come here and then gave lectures, not this kind of lectures, but classroom lectures also. And in the initial stages, practically all professors of IISc, Professor K.P. Abraham, Vasu, Dwarkadasa, D.H. Shastri, Y.V.R.K. Prasad, all these people had come here, gave lectures for the students, because initial stages there was no faculty. We are relying on IISc. Then I.G. Karkalpakam. Again, we had a sort of a battalion type people, lot number of people used to come, starting with Placid Rodriguez, Baldev Raj, Jnanamurthy, Sardarilal Mannan, S.L. Mannan, R.K. Dayal. Like that, there are many, Kamachi Mudli, our own student. No, he's Trichy, sorry, another person is, what is his name? Huh? Vanson, right. Then, no, what is his name? Kamraj, no? He's IIT Madras, Kamraj. There are many people who have come from the IGCAR and IIT Madras, not many people gave here lectures because only the mechanical faculty member used to come here. Then from RRL Trivandrum, we have BC Pai, Satyanarayana. Those are the people who quite frequently used to come and give lectures to our department. All this is because of Professor T. Ramchandran. And we youngsters could interact with those people. And, well, this interaction helped us in getting external funding for the development of the one. I was a BRNS member because of Professor Placid Rodriguez. Right? Like that, we could get BRNS project here, ARDB projects here. Like that, there are, because all this is because of Ramchandran recommending us, say, these people can do that work, why don't you help us? This is he used to tell. Then afterwards, I think one or two anecdote type thing that we used to go to tea, everything, and he used to tell. See, this Samudra Darshan, where you go there for your coffee, if at all you are going, tea cannot be spoiled beyond a limit, whereas coffee can be. So he will say, Sudhakar, we'll have tea only. This is the type of things, so free with all faculty members. That quality, later I worked elsewhere also, not in after my retirement, but I didn't find in those institutions this kind of relations are there. Then he used to tell, he used to come in his Herald 2-door blue colored, green colored car, Herald car, Standard Herald in those days, and he used to invite us to his house. He says, my wife has prepared payasam and I don't like it much, and if I don't eat and bring you people to eat this, she will keep it in the fridge and give it to me tomorrow again. This type of, free talk he used to do with us, and then always treat us very well. We can't, I can't remember anybody who has treated the junior staff in this institution like that. There are only two people who used to, another thing that I have to tell, maybe Subhash will agree. In those years, assistant lecturer is the untouchable type of things. Lecturer also won't talk to assistant lecturer. He will try to talk to assistant professor. Assistant professor will try to talk to professor only. It type of this watertight compartments were there. Only in the metallurgy department and chemical engineering department of this college, everybody used to talk to all. Otherwise, our duty is to tell seniors, good morning, sir, good afternoon, sir. They won't even respond that. This is the thing, it was there earlier. But metallurgy and chemical, when it started, picture changed. Slowly, everybody also realized that things should be different. They are also like us. Maybe that we are aged, senior in age, so we are at higher position. By our age, those people will also be like us. Therefore, they have to change, and they did change, this type of thing. So people must have seen that. So Ramchandran, that era, 80 up to 89, from 1965 to 1989, it was a sort of golden era for the department of the metallurgy. And about the genesis, I think Suman has already told. We in 1990, we started thinking about conducting that international seminar. We could save some money in that, and then there are well-wishers, both his colleagues and some students. Nagprakash Babu, whom you referred, was the first batch student. All right. He did MTech also here. Then they gave a lot of donations, and then because of that we are sustaining. Even during COVID time, it was continued by I mean, what should I say, conducting 2 lectures in one particular year. So that for 35 years, 35 lectures should be there. It is that way it has been done. Earlier year, there was one Professor Surendranathan also. He has not come here. He is in Trishur, somewhere, yeah, very close to that place. He used to keep accounts, and then he used to help Dr. Prabhu. And I should thank here Dr. Prabhu for almost single-handedly working to keep this lecture series continuing. Because of his good effort, we have seen in that. So thank you, Dr. Prabhu, and we hope this series will further continue, because all other departments which started this kind of lecture series ended miserably. They had, the lecture series had a very early, I should not say death, but it got stopped. It was that. Whereas only this one is going. That shows, and somebody, I think Professor Ergal only remarked, could see so many students attending. Whereas for other such thing, you started, hardly handful of people used to attend. And this is the one which is having a good attendance and good people who come for this, they are very noted people, and they have done. And now that another DMR person, head of DMRL person is coming, we can still have interaction with them. Yeah, with this, I think I should make space for others to speak. Right. Thank you.
Thank you so much, sir, for sharing such wonderful moments with us. Now, I would like to call upon Professor Bhalal to come and share his memorable experiences with Professor T. Ramachandran.
Friends, good to be on this side of the stage, I was here back in 66 to 71, sitting on that side. Okay, so it's good to be here now. It's nice to be back in Surathkal, NITK. I'm sorry, I'm coming in the way of, I'm delaying your interaction with the with the chief guest. So let me be brief. Among the people here, I am the first student of Ramchandran. Okay. And the first lectures I took was not in metallurgy. He was teaching those days German. And it was great fun. You can imagine somebody teaching German in Malayalam accent. It was the talk in the hostel, What did he teach today? Fräulein. We never got that right. And he would insist for half a class, say, no, not like that. And then, of course, those days, I did several classes with him. For example, there was a full course on ternary phase diagrams. I'm very thankful to him because that gave us, of course, he had already made wire models to show us. But, ternary phase diagram, I don't know whether metallurgy students will have seen any of those. Ternary phase diagrams is a 3D imagination. And the imagination that Professor Ramachandran gave us served me all through my career. Among my colleagues or among students, my 3D imagination was always took its place. Then, of course, we did physical metallurgy 1, physical metallurgy 2, and so on. So I did several courses. Those days, he used to teach several courses. Excellent teacher. I am not a physical metallurgist. I used to say that any time the metallurgist solidifies, I am not interested. I'm a pure process metallurgist. But then whenever I had to talk to a physical metallurgist, during research you have to do this. Ramchandran always came back to me. I would still remember what he taught in the class. And, from those days, it was from Reed Hill. So. And the other thing is that it may be the different case now. We in metallurgy, see, I came to metallurgy in spite of the fact that I could have got into any other department, including electrical, those days electrical, mechanical, whatever. Metallurgy is my first choice. And Professor Ramchandran made it worthwhile. We held our head high in the hostels, not the kind of feelings that you have here, okay? Because our department had maximum number of PhDs. The level of courses are very high, and so on. So, so we were very thankful at that time. You talk to any of them, first, second, third batch people. We were very thankful that Professor Ramchandran shifted from IIT Madras to KI. So those days, it is their loss and our gain. Ramchandran was a different kind. I'll just tell you, of course, he just gave that introduction. I'll just tell you one instance and then I will stop. Ramchandran taught us thermodynamics, metallurgical thermodynamics. You all done, most of you have done thermodynamics, isn't it? So, most of the time you don't understand. You somehow try to crack. it. I got 85 or something out of 100. But so we did a lot of thermodynamics. Mechanical engineering taught us thermodynamics. So the Sudhakar Naik taught me in chemistry, physical chemistry, thermodynamics, and then Professor Ramchandran taught us in fourth year. And then I went to IIT Kanpur, and then IIT Kanpur insisted that those who come from IIT, outside IIT system, has to do the undergraduate thermodynamics again. So I did that. And then that semester, there was the Bangladesh war, I had come, and I came to the department. And he asked me, Ramchandran asked me how is it going, etc. And I told him, sir, now that I have done this course in thermodynamics, my understanding has improved. It was such an insensitive talk, a 21-year-old, certain amount of arrogance too, I think. I did that, and he said, how was it and all that. He asked me how was it taught and which book, this, that, all that. And then next year, IIT Kanpur held an QIP course, that intensive course. And I'm walking to the department and I see Professor Ramchandran. He had come, I thought he has come to give a lecture or something. No, he has come as a participant. And he told me, you told me your understanding improved. I want to see how they teach. This is what Ramchandran, an epitome of modesty. The fellow who worked in Germany on texture, now everybody talks about texture, this OIM, etc. He worked on texture with those manual XRDs, manual XRDs where photographic papers are exposed and so on. So back in the 50s, but he's the shloka saying Vidya Dadati Vinayam. He's the epitome of that, Professor Ramchandran. And fairness. So modesty and fairness is something that you would, all of us need to have learned from them. And I'm sure many of you have. Thank you.
Thank you so much, sir, for sharing experiences with us. I thank Deputy Director, sir, and HOD for their presence. Now, may I request our chief guest and speaker, Dr. R. Balamuralikrishnan, to take the stage for the 35th Professor T. Ramachandran lecture.
Kumkum Banerjee, all the senior superannuated people, I'm really honored by your presence, all of yours, current faculty, all students, a very good afternoon to all of you. And it's been my privilege to come here. Finally, even though I've heard a lot about NIT Surathkal and have interactions with many, many people, but this is my first visit here. And so I'm really overwhelmed by the introduction that was given and the sense of the occasion itself, as was told by two previous people from here about Professor Ramchandran. And indeed, it was very stimulating and invigorating to hear Professor Ramchandran himself on the video talk about this, and his passion and what he has done for this place is all too visible to see. So while I'm overwhelmed by this occasion, it's also my duty to try and see if we can transmit a little bit of that kind of a message across here. And when Professor Kumkum Banerjee asked me to do this, so I was asking her what it was. So I think at the very outset, I'll pay my respects and apologies to all the senior people sitting in the front. So probably there'll be nothing new for any of you here, sir, but the whole idea was to stimulate the younger minds and show them the connect. Professor Balal just now said he could have picked any branch, but he picked metallurgy. But these days, most people come to metallurgy because they could not go to any other branch. And even after coming to metallurgy in the morning, we were discussing everybody wants a software job. So the idea is to show you that you can do metallurgy and still do software. And your job need not be just software. In fact, I keep telling people that we are all hardware plus software. And just software won't work. So if you all have to travel, see, you can play a game virtually, you can have VR machines and other things, but as long as you are human beings and you need to travel somewhere, you will have to travel in a physical car, not in a virtual car. Right? Even if it's a single small pod, the size of that pod should be big to accommodate you. So there is certainly things to do in hardware, which does mix with software and with technology, and now AI is the word for everything. The idea is we should not forget or lose human intelligence in our pursuit of artificial intelligence. When they are trying to make robots human, humans are trying to become robots. Right? So that is something that we have to arrest. And all the people sitting here in the front are prime examples of, in terms of what difficulty, how they've come, they've set things up. And now it's for all of us, and the country is at a crossroads. So especially the younger generation who are here, of course we keep hearing Atmanirbharta and Viksit Bharat 2047. And not only that, I mean, you have very well seen that just in the last maybe 2025 alone, how much the geopolitical scenario has changed. Who is helping, who is friend, who is foe in the international context, nobody knows anymore. And we will have to do what is necessary, what is essential. And also it's trying times even as individuals, but primarily more as country and also as individuals, what we need to do. I think that is the task in front of us. And so probably over the next hour or so, I'll just take you through this. And the idea, like I said in the title, is from atoms to applications and unlocking the thrilling powers of material science. The idea is, of course, now metallurgy word has been replaced by, it was initially metallurgy and material science, and now it's all just material science. And well and truly metallurgy is a part of material science. So with this introduction, I'll just get going and we'll see how this pans out. Okay, I think I've spelled Professor Ramchandran's name with an extra A. It's revenge probably for most of the people missing the A in my name whenever I give talk, and they'll write it as Balamuralikrishnan. Okay, so I think there's an A compensation that happened there. I apologize for that. So this is again an acknowledgement to a whole bunch of people. As you will see from the talk, there I've worked with many, my biodata was read out, so I am from IIT Madras. And yes, to respond to Professor Ramchandran's message, yes, the namesake in Carnatic music, I also revere him, but my interest is confined only to listening. I can't sing for any anything that's worth. So but I do listen to my namesake a lot. And yes, Professor O. Prabhakar was head of the department at IIT Madras when I was a student. And so like I said, many agencies worked with us, we will see. And one of the ideas was to go from what is taught. In fact, again, a lot of mention. Yeah, anything? A lot of mention was made about moving from teaching to research. And it is now moving from teaching to research to product or applications. It's okay, I think we can do it here. So that the acknowledgement was more for my institutes and my own teachers from high school, Professor Vasudevan at IIT Madras, who inspired me to be in metallurgy and continue to do what I do. And for some reason I developed this fascination for steels when I was a second year BTech student. Metallurgical thermodynamics was mentioned. Say Professor Srinivas Raghavan taught us metallurgical thermodynamics and physical metallurgy 1, just taught by Professor Vasudevan from Reed Hill again. And so that has stayed with me till date. And Professor Garrison, who was my PhD advisor at Carnegie Mellon, Dr. Arunachalam's name, Banerjee's name, Dr. Malkonde, all were mentioned here. Dr. Muralidharan, who was my first boss. And I also draw another inspiration from a very senior person, Professor V. Ramaswamy, who was came and who was heading SAIL, RDCIS, then the Salem Steel Plant. And till date, I think he's 86 today, and he goes to PSG college, goes physically and takes and teaches graduate courses. Until 2 years ago, he was teaching undergraduate courses. So these people are all inspiration for us. And when we compare to them, they are towering giants. And we just try to do whatever little that we can do. So of course, since the talk will primarily be about steel, it's about that. And of course, I've had several batches of students, including from here, a few MTech students who were with us to do some of the work that we did, and all the past directors of DMRL. So I think the idea is to delve into the world of materials, see what materials are, see what material science is, how that takes us into materials engineering, how that helps us find final products which are actually used. So that is kind of the theme. So, and since there are a lot of students, so I think we like to keep this interactive, right? So what do you see there? And clouds, right? So what is the scale of the clouds and size of the aeroplane? So just keep thinking about this, right? Which is bigger? An aeroplane is bigger, or a cloud is bigger, or a set of clouds is bigger? Set of clouds, right? Beyond that you see the sky also, right? Do you think you can put an estimate on the sky size? Right? People do say the sky is their limit. But what are they actually saying? Keep thinking about that. Okay? So what do you see there? Okay, so atoms. So there is nucleus, which has protons, neutrons, and electrons. So that's on that side. Okay, so you see that is smaller than anything that is seen on the picture above that? Yes? What do you think this is? Galaxies. Very good. Galaxy, right? Okay. Now that? Good. By extension, people said cluster of galaxies. Had I put that on this side, you would have thought it's just a bunch of fireworks or light. Correct? So placement of things actually influences what you think about it. Okay? But yes, but this is actually a picture of a cluster of galaxies. And so this is the physical realm as we know it. It spans several length scales, from subatomic particles to atoms to galaxies. All right? And the universe, nobody really knows how big it is. People are still trying to find out. There are some estimates. And it's ever expanding as we know it. Right? And if you go from even the size of one proton or one neutron to the largest known dimensions that we have, you are looking at something like 13, very, very large orders of magnitude, okay, differences. And again, for students, if you want to look at what an order of magnitude is, try lifting a 1 gram, a 10 gram, then a 100 gram, and like that, suddenly it becomes 100 kgs, right? From 1 gram to 100 kgs is not very many orders of magnitude. So imagine when you say 13, 15 orders of magnitude. And all of us learn Avogadro's number 6.023 into 10 power 23. And today you don't even remember, you ask Gemini or Chat GPT and it tells you. Right? So imagine you should get a feel for what those numbers are. And incidentally, the physical world is a material world. And so I want to ask you this question. Can you imagine or think of a physical world without materials? Right? So whether you study it or not, materials are inherently important to human beings, in fact, indeed to whole of the existence itself. Right? So where does our study come from? What are we studying actually? So if you look at that as materials over a length scale. Now if you look at materials over time, This is something that goes from 10,000 BC up to about 2020, and different types are there. Since I have to cover a lot in about an hour, I will not spend too much time on each one of these individual things, but you can see you have, of course, civilization has been defined by materials, right? Stone Age, Bronze Age, Iron Age, so on and so forth. Even what you call as information age or AI age, these are all driven by your semiconductors, electronic materials, optical communication, your fibers, optical fibers, your 5G, 6G networks. Yes? So without materials, you really can't think of any of these innovations or advancements. So that just shows that the different classes of metals, materials in terms of metals, polymers or composites or ceramics. And by and large, you will see that there are more natural materials on the left, whereas there are more engineered materials on the right, especially in the last 50 to 100 odd years that we are looking at. So what's to come in the future, it is in all your hands, actually. What we can do, what we will have to, what new materials we discover. And in a couple of slides, we will see that also as to what that is there. So what is this? Good, easy enough. This, cars and roads, and great, and I hope the pictures is visible. There is also a divider in the middle, right? So again, you show a picture and you see what is it? As much it reveals about what is there, it also reveals what your thought process is. Right? Again, we saw that about the galaxies and fireworks and light. You will see why I am building this story up this way as we go along. Right? See, we could also say, for example, there are lane dividers there. That's paint, that's color. Everything is there, correct? So I'm just basically driving, which was all the vogue earlier. Some of people thought it was bad and it went out of fashion, is to do descriptive learning, both in terms of absorption and in terms of communication or conveying, right? So if you put fill in the blanks or multiple choice questions, then actually your brain shrinks. It does not expand, it does not think, it's not free enough. Okay? And when all these stalwarts, great teachers that they're talking about, the great teachers made you think. They just did not give you information, even though the information tended to be descriptive. Right? So what is that last one? So it's a power reactor, it's a nuclear reactor. Okay? So the question is, what do we need to make these things? What do we need? Very good. Not just materials, we need engineered materials now, correct? So, that's then welcome to the world of engineered materials, which is what material science and engineering is about. Is there anybody here who is not a material science and engineering major or not in the department? Okay, 3, 4 hands. Okay, fine. Of course, sir, yes. But all of you would still deal with materials. I don't think anybody will dispute that. Yes? So, this is basically what we look at in terms of what we are doing. So, now this is therefore the metals that are there in a smartphone. And I put most of my slides from what is easily available on the internet. You can go and take a look at it. Right? All of you have a smartphone, right? So, you look at the number of elements that are written there. That's about 6, 9, 11, 14, 17, 18, 19 elements are written. In addition to the more common ones are not mentioned. Okay? So there are something like, in fact it is told that you need about 52 elements of the periodic table are involved in one way or the other to get the smartphone that's there in your hand. And of course these are the more important ones that are actually there in some part. Okay? So I hope at least the people in material science have not forgotten the periodic table. Yes? So this is a periodic table and we have metals, non-metals and metalloids. We have all of these, right? So now we move to car. We saw in that picture we saw the phone, we saw the car and we saw the nuclear reactor. So these are the different materials that I use in the making of our cars. And very broadly, if you see as a class, as a family of materials, the on the top right, you will see that the amount of the metals component has kind of gone down over a period of time. Others has increased, so also have plastics and rubber. Okay, so, but these are the different materials that you need to make a car. And this is, of course, the nuclear reactor. I think this thing works good. Yeah. So you will see that this is again just a whole bunch of, I think both Professor Banerjee's names and Jim Williams' names was mentioned today. So I think this paper is written by them not too long ago, about 10 years ago. Right? And you will see that there's a whole host of materials that are present in a nuclear reactor system. Okay. So it shows that these engineered materials, what we looked at, they're all pervasive. Incidentally, anything beyond the earth, maybe if you leave the space station and the few spacecraft that are outside, are there any man-made materials in outer space, in galaxies, in the universe? Are there any? Are there any? No, right? So while we talk about engineered materials here, all the materials that you see there are in some sense natural materials, right? They are natural. You do not know how they came, what happened. I mean, if you read something, for example, there are planets, I mean, where there will be a rain of, helium, there will be rain of something, okay? You will have diamonds all over the place, yes? So it's a very, very what creates the materials, we saw the periodic table, that's as far as we know. Okay? But within what we deal with and what we are interested in, like how do we make things? Right? It's different from what nature has made. It is there. And we can also use that again towards the end, there will be convergence of both these ideas. So whether it's in the space sector, defense sector, atomic energy, wherever we are, basically everywhere materials are there, the engineered materials. So just to sum this up for ourselves, so this part is essentially to give all of us, especially the students, a grounding or a framework from which we launch on why engineered materials are important and what we do. First is they are ubiquitous in today's world. That goes without saying. We just saw how many materials are needed for the smartphone, how many are needed for the nuclear reactor and so on. There are more engineered and advanced materials in use today than at any other time in history. Okay, and I'll show this with numbers in my next slide. In spite of that, the need for novel and even more advanced materials which can perform under extreme or hostile environments is equally high. For example, many of you will be aware that India is trying to put its first, the Indian person, second person went to space just now and came back, but we are trying to launch our own space station. Yes. And want to send people in space, and the kind of materials that you need to do those missions. And eventually people are starting, already US, there are a couple of programs in other countries as well to start sending a mission to Mars and to try and see what it will take for people to live there for a period of time. Okay? So these are extremely hostile conditions, and you cannot possibly carry everything from here. So how to make use of the materials that are present there. In fact, this was another reason I asked you about in the other parts of the solar system, in the galaxy. The material that is there is not something that we made. Right? So, but what is there, how we can use. That means slowly our interest is starting to extend beyond what we have on planet Earth. But still, even here for us, for the work that we want to do, we need more and more novel and more advanced materials and which can perform under very extreme or very hostile conditions. And this still demands the design, discovery, development and deployment. This is called as the 4 Ds of materials. Okay? The design, discovery, development and deployment. At a very rapid pace and of course at reduced cost. This is therefore the goal overall for the field of material science. It does not matter whether you're in academia, whether you're in industry, whether you're in an R&D institution like us. But essentially, this is what drives the field. So this is what I was telling about, and again, this is going back to this Fleck, Deshpande and Ashby's paper of 2010, where this is probably what's called as an Ashby map, where you can plot two properties and then put all the known materials within in that as some blobs or envelopes of different materials. And so what was told is until about the 19th century, we maximum had less than 1,000 materials, a few hundred materials, okay? But in the last 100 to 150 years, that number from 1,000 has gone up at least to 1,60,000. Today it's probably closer to 1,80,000, 1,90,000, maybe even 2 lakhs. Okay. And this, why I put this particular picture is because you will see that I'm sorry, you will not be probably able to read from there, but many of these elongated, this stick kind of stuff is because we have engineered the same material. The x-axis, by the way, sorry, is density, y-axis is strength. That means the same material, we have been able to play with its density through different mechanisms, through engineering, through what we do, and develop new. For example, if you make an aluminum foam, it's much, much lighter than aluminum itself, right? But it is still aluminum. It's aluminum and air in some sense. Okay. So you will see that these domains have expanded over a range of strengths and densities as opposed to having a much more narrower distribution. This is another testament to human ingenuity and our ability to discover or engineer, invent new materials. Yes. So, for the purpose of this talk, because like I said, I've titled it as Atoms to Applications. So, I will be repeated. Atoms to Applications, this is one. From lab to product is another. It could also be called as concept to product. But ultimately, what we want to do is we are trying to take something with the intention to find some useful application for the same. Right? So, again, this is not a very tight definition. This is just for the sake of students, just to keep ourselves with some grounding. What I will call as science is lab scale studies and activities to develop materials and processes on a very small scale, and also to obtain understanding of the material's behavior, what we call as structure property correlations. And of course, we'll look at this in the next few slides. Whereas what we call as technology is the ability to manufacture these useful products on an industrial scale reliably and time again. Right? Not just once. You want to do it over and over again. So this is something that all of us are very familiar with, which is a material science tetrahedron, and where we have processing, structure, properties, performance, and in this particular one has characterization in the middle. There are different versions where you can put so many other things in the middle as well. Okay. So the whole question then is, this is what has been our work, our driver, our guiding compass, if you will, of our work is this tetrahedron. And we'll go and look at it in a little bit more detail in the coming slides, but structure is how does it look like and what is it? Properties, you understand all of that, processing, so I will not spend time explaining this particular slide. And more importantly, the processing controls the structure gives a certain set of properties, and then the properties design the performance for your intended application. And that is a cause and effect this way. Equally so, if you want a certain performance, you work backwards, right? So this is the inverse problem in that case. So same thing put differently. This is a typical R&D activity. You have a particular application. For that application, you need certain performance. To get that performance, you want to achieve certain desired properties. And you get those properties by doing microstructural engineering. That's because we know of this processing structure property performance correlations, right? Now we have a few things at our disposal. We can design the composition. This is practically an infinite set. Okay, it is not a limited thing. But very often practical considerations would bring it down to a smaller subset. Okay, something like the Ashby maps you can use, some figures of merit you can use, and so on and so forth. Can do. Then for a given composition, if the material, and this is more true of metallic materials, you can do the so-called thermomechanical processing to change the properties. Heat treatment is also there. Conventionally, the difference between these is there is no deformation or stress applied when you do a heat treatment. It is only application of temperature. So I want to look at this characterization paradigm because I thought this will be useful for the students. Because regardless of whatever you work with, even though I kind of came up with this maybe something like 15, 16 years ago when I was teaching this course at the University of Hyderabad. But later we realized that this can be used for anything. And today morning also I had the chance to visit several facilities. And if you look at it fundamentally, this is almost a reductionist approach because you can use this one thing to get into very, very complex problems. So you have a system, right? But by characterization, you're just trying to understand something, right? So we will take structural characterization as an example and look at it. So you have a probe, which then, it questions the system with a certain stimulus. It could be optical, there will be light. In an electron microscope, it is electrons. In an X-ray system, it's X-rays, and so on. So and the system here could be the material that you want to investigate. And then the system creates a lot of responses, right? So for example, if you bombard the metal with high energy electrons, then you can get secondary electrons, backscattered electrons, you can get characteristic X-rays, you can get inelastically scattered electrons, X-rays again, right? So many signals you will get. So for example, in the case of a structure or a microstructure, this looks like a mosaic tile, but this is also the microstructure of a titanium alloy, okay? So we are then looking at morphology, what is the size, defects, what are the phases that are present and what is their distribution. And primarily, you can get analytical, which is the chemical information and the bonding type information, and crystallographic information. Crystallographic is of course what is the crystal structure, point group, space group, orientation, so on and so forth. But essentially you can use this paradigm, this part, to look at anything. Suppose you want to look at mechanical properties, right? In a tensile test, what do? You apply the load and you see how the material deforms. And from that you're able to get its modulus, you're able to get this yield point, ultimate strength, percentage elongation, so on and so forth. In an impact test, you hit it with a hammer and are able to find out how much energy it absorbs, okay? So there is always a stimulus and there is always a response, and you need to have something to measure the response. Why I put this is because the structure is so inherent, and in many of the advanced materials, the microstructure is inherently multi-scale. Remember we talked about subatomic particles to galaxies. In our engineering materials, whether it is steel or nickel-based superalloys, surprisingly what happens at the scale of atoms or the assembly age of atoms controls the macroscopic property of that material or component. Okay. So this is the beauty. Rather than doing your work routinely or without, see, that means you are having the power somehow. That is why I put that as unlocking the thrilling power of material science, right? You can literally unleash it by playing with it. I mean, in some sense, with materials, you're playing God. You're trying to do something and change its properties. But to do that, you have to understand what's happening. Not necessarily in the same sequence, but you need to have a good grip of what you're doing and why is it having the effect that you are seeing it as having. So this is just basically by the naked eye, and if you can look at the scale markers, this is again a very old slide, but I've left it like this because I thought nothing else conveys it. See, from here to here is a linear factor of 10. That's 10 micron to 0.1 micron, so that's a factor of 100. That's 0.1 micron, which is 100 nanometers to 1 nanometer, so that's another factor of 100. So you are seeing a 10 power 5 to 10 power 7, that is 7 orders of magnitude differences in these here, right? And of course we can also go and look at individual atoms in an atom probe. So this was again because DMRL we installed the first atom probe in the country way back in 2005, and this is a FIM image of tungsten 110 and the crystallographic poles, because the atom tip happens to be exactly like your stereographic projection for all of those of you who have come up to that point. And each dot here actually represents an atom, okay? So I will not again get into the details because I know there are students from second year, third year and onwards, and you may not have seen this. But I mean, this is really, really exciting, right? I mean, if you can look at that central one, you will see that it eventually disappears. And because the corner atoms grow bright because of the electric field, which is very high. And this field ion microscopy is something that our Professor Ranganathan from IIC did way back in the early 60s. But later, this got integrated into the atom probe. And again, modern atom probes do not have the field ion microscope. But you can see that, you can see in a 110 plane how the atoms are arranged and what is the atomic sequence. Okay. So now when you go to the atom probe, you are able to look at how the individual atoms are there. This is again how the vanadium atoms are distributed in a steel, and all those elongated particle kind of things that you see are actually vanadium carbonitrides. This is again some work which I did in Northwestern University in 2009 in Professor Seidman's group. Of course, today India has 3 or 4 latest generation atom probes with which we can work. So this is the atoms part of it. Few more pretty pictures. This is from IBM. I think these are actually the atomic force images of a nickel 110 plane. Okay. So each one is, you can see actually how because this is from an atomic phase, scanning tunneling microscope image. And therefore you're looking at the surface fields and you're able to, each of those tips is one nickel atom. Okay. So this is the crystallography that's shown there. And these are very old things. These are more than 25 years old. But this was the first time that people were being able to manipulate individual atoms. In fact, they moved xenon atoms and placed it on a nickel surface in those cavities. And they wrote IBM with xenon atoms on nickel. Okay. So now from the atoms towards the applications, which is the main focus of the talk. Right. So for that purpose, I'm using this word translational research, because you'll find these words coming up often, and so you should not wonder what it is. Again, so we are looking at migrating fundamental knowledge, again thermodynamics, phase transformations and microstructural engineering, which form the basis of our understanding, from lab scale experiment to industrial scale production. This is from lab to product. And I'll take one particular example, which is where I have worked last 25 years, which is high performance naval steels, to illustrate this. And the idea is to just show how you can use what you do in the lab and take it to a product and actually have the product being realized. This is one such example. Okay. So the story goes back to the late 1990s, and we wanted to build our aircraft carrier, and we could not get the steel for it as India. Okay. And until that point, we were what was called as a buyer's navy, not a builder's navy. So we have ships from UK, Germany, Italy, so many countries, Russia, and we were only doing repairs and refits with small quantities. And the steel that was required, nobody was giving for those also. And more importantly, to build I think once it goes into sleep mode, this happens. Right, so the steel was not there, and then so they approached DMRL and said, can you do it? So that was a challenge that we took up. And oh, this is a long way further down. You can't do this. Can you go in and get out? Okay, fine. Go ahead. Yeah. So this is actually an image from Operation Sindoor last year. Okay. You will see this is the carrier group. You can see so many vessels that are sailing along with Vikrant, which is in the front. And so this is, like I said, this is a 2025 actual image. Okay, photograph actually. It's not an image. It's a photograph of INS Vikrant. And so starting from that late 90s work that started, Vikrant, of course, we started supplying steel in 2005, 2004. And like it was launched in 2013 and it was commissioned in September 22 by the Honorable Prime Minister. And this has taken This is all Indian steel. So at the time we had 0 kgs of steel, our steel being used, whereas this alone has about 22,000 tons of our steel, including the flight deck. The flight deck has to be extremely flat because the aircraft has to land and take off from that. In fact, it is 3 times more stringent flatness than normal steels. And this is something that we have made it. So the remaining part of the talk, almost except for the last 5-10 minutes, would focus on how we did this with the idea, with the hope that you look at how this interplay between lab work and industry, between science and technology, actually helps us realize products. Okay. So we go back and look at the marine environment. And again, I will not go over the details because I just wanted you to get the main message, and each one of this, potentially there is material here for at least 10 hours of talking, If you take 4 slides here, I've given an hour's talk or 45 minutes talk on just those 4-5 slides. So I will not do that, but anybody who's interested, we can discuss subsequently. But the whole idea is the marine environment is also one of the hostile environments because there's a lot of, obviously salt water is there. You are not on land, first of all. You are far away from shore in most places, most times. And as it is, the operational conditions are something like this. Okay. And there is always wave movement, so that means there is always cyclic loading and so on and so forth. And therefore material selection is dictated by many of these factors. Just to give you an idea of the different size of steel vessels that are built, you can see that some of them are more than almost half a kilometer long in oil tanker. Okay. Again, you see geopolitics comes and plays in strange ways, right? After this very recent US-Venezuela thing, I think they've also seized a tanker, right? Russian tanker, which is carrying Venezuelan oil, right? So overnight, something what you can do suddenly will become not possible. But anyway, incidentally, that is the oil tanker, and you have an aircraft carrier, that is the USS Enterprise, which is 341 meters. Our Indian carrier is much smaller. Okay, INS Vikrant is much smaller. So these are the different types of naval vessels. The aircraft carriers, other warships, submarines, underwater platforms, support vessels. Again, why I put this is because for wherever metallic material, steel is used, once we did that work, from 2007 the Indian Navy said all our ships, whether it is support vessels or warships, will use Indian steel only. Okay, and that is why we are able to do that. But that's an aside. In terms of the materials that you need, because there are structural and propulsion materials, then you have paints and coatings, and you have several functional materials for different sensors and actuators. But the fundamental point to see is metallic, ceramic, polymer and composite materials are all required. And sometimes as students, as kids, we say, is steel better or aluminum better? It is like asking, is pizza better or pasta better or burger better? I mean, in some sense. Then somebody will say all of that is junk food. Eat only carrots and beetroot. Okay. But when it comes to materials, you really have to look at what is the application. That's why I had that slide. And in today's scenario, there's a room for everything. And even though I will not touch about it today, sustainability is very, very important. Okay, so I'll just mention it here a couple of minutes and leave it at that. But when all the students, the youngsters, you are looking at newer materials, because the rate at which we are consuming resources from the planet is alarming. As it is, something like 25% of the planet is irrevocably damaged. Irrevocably damaged means we should not touch it for another 150 years for it to recover. Since that is not possible, we are actually living on 0.73 of a planet. We don't even have one planet right now. And if all of us want to have, Western kind of lifestyles and so on, by 2030 we will need 2.5 planets, 2.5 Earths. And by 2050 you will need 5 Earths, whereas we don't even have one. So our drive towards material, again I did not put it there. Some of it could be revisiting older concepts, the so-called 3R, reduce, reuse, recycle, that became 6 Rs, that became now 9 Rs. That's a whole different field by itself. And I think a talk I gave in Kanpur was entirely on that, materials, prosperity and sustainability. So that's another big driver, not just the technological demands, but how in fact, incidentally, why people are so serious about exploiting Mars, Moon and all, is simply because at least in an emergency you need to be able to go there and get something or be able to go. But if we continue at the rate at which we are doing right now, again we have about a 15 to 20 year window is what people are predicting, and by that time if we don't restore sustainable means of living, of utilization, of exploitation, then we may be on a totally degrading path. And beyond about, these are some people will call it doomsday predictions, but at least part of it is very real. We may have only 40 to 60 years on this planet for the planet to be livable. And when people say livable means it's for human beings, the planet will stay, right? 99.9% of the species that have ever been on the planet have gone extinct. The planet has seen asteroid impacts, has seen so many things. People say that the moon itself was a part of the planet and just got bumped off long back. So when we say it is dangerous, it is not dangerous for the planet. Planet will be there. It's dangerous for us as human beings, as a human civilization, right? So that's very, very important, the aspects of sustainability. Okay? So whenever we look at newer things, how sustainable is it? What are we doing to it? Is it available? So one of the bigger drives, therefore, is now to use more earth-abundant materials than use rare materials. Okay? All those is another part of the research, but I just wanted to explain this. So in terms of naval material structural, again, you have steels, aluminum alloys, composites, foams, so many things. This is what I will focus on in my talk. Right? We will look at this. And at least for these two classes, which are fairly large, today there is no substitute to steel. So they are built with steel. Okay? Special steels, advanced high strength steels. This is again from 2012. Most of you would have seen this. This is March. You can see the date there. That's March 26, 2012. James Cameron went down to the deepest point that is known in the ocean. That is the Marianas Trench, right? Which is almost 11 kilometers down. Okay? And the important point here is that the pilot's chamber, which is here, uses steel which is 64 millimeter thick, because that is the shape which can resist the pressure the most. And if you want to make it into a cylinder which is normally the shape of a submarine, then the calculations to withstand the stresses shows that the wall thickness should be 192 millimeters. Right? You can imagine how heavy that will become. Anyway, this is what it was. And I think to give you a break from my speech, while that was there, now India has its own program. Anyway, the whole idea is that India has a program. This is the steered by Ministry of Earth Sciences, the National Institute of Oceanographic Technology in Chennai. And this program is called as Matsya 6000. Okay? So the idea is to send 3 human beings down to 6 kilometers depth in this vessel. And this is an ongoing program. This is a national mission overseen by the National Principal Scientific Advisor to the Prime Minister, but being being steered by the Ministry of Earth Sciences. Anyway, so that program they are working, what I wanted to show you is that they'll show you what it is, the concept of that, and how it will be launched from a mothership, and how it can go down. And I just wanted you to see it as it's a phenomenal engineering challenge. And it takes multiple expertise, it takes a multidisciplinary approach. Therefore it will be multi-institutional, cross-disciplinary kind of work. So they are doing VRX, helping them with something. You need to electron beam weld titanium so that it is able to withstand all those pressures that come on that system.
6000, a deep water manned submersible to take 3 human personnel to the hadal depths of the ocean. This manned submersible is being developed by National Institute of Ocean Technology, NIOT, under the Deep Ocean Mission of Ministry of Earth Sciences, Government of India. Matsya 6000 is an underwater vehicle capable of underwater travel to a depth of 6,000 meters. The underwater travel duration can be for 12 hours in normal conditions and 96 hours in abnormal situations. Matsya 6000, which is 10 meters in length, and 3 meters width, 5 meters in height, weighs 28 tons in air. It floats in seawater with a positive buoyancy.
Okay, so I guess you could not see that, but basic idea was that they're going to take that down to 6 kilometers inside, and then so you can imagine what the kind of engineering, and people will stay there. I mean, it's a several-hour mission that they're trying to do more as a demonstrator, and in the future, longer duration, things that can take more people, all that will be built. So as it is, it's a very, very challenging endeavor to do that. Again, in terms of steel, so now I think I'll probably rush through this in about 10 minutes. I will not do much more than that. The whole idea is what are the properties you need and what steels you want. So this is just going to be, I'm trying to compress the about 15 odd year story in something like 5 to 10 minutes. Okay. So, but the whole idea is the stage has been set, and just to tell you that what you can repeatedly go back and forth between lab and industry to actually produce a product. And today it is doable because as DRDO also we are very consciously and strongly establishing interactions with industry and academia, institutions such as yourself. And therefore, you can also get to be a part of a project based on your work, research work, whatever it is, to be able to involve in seeing how it gets applied eventually, if not immediately. So this is what we do in the lab. So again, this is primarily for the students, just to tell you that again, from teaching to research, so your understanding of the knowledge to actually doing the work and developing new knowledge, and how that new knowledge gets applied in terms of developing material solutions and products. Okay, so we have a lab scale, and you have alloy design and processing, you have homogenization. This is again with respect to steel, but it's equally applicable to other classes of materials, only the numbers may change. Okay, so fundamentally in this case, we were able to establish a resilient, robust manufacturing base for the steels for these critical applications. And so if you do in the lab, this will be the literature survey. Many PhD students would relate to this, what you want to do, right? And in this particular scale, we use some thermodynamic design to narrow down the compositions. Then we actually process, which means we melt, forge, and roll 2 plates within the lab. Then we do several heat treatment cycles to find the optimization. Then we measure the properties. So those 2 arrows, that is the characterization of structure as well as properties. And then you repeat the cycle, right? So this is what was done. This is again the physical metallurgy and process optimization, how you can do, that's what this talks about. And we looked at this earlier, right? So now this is the first phase. But in the second phase, what you can do is you can take this and start looking at scale-up issues for industrial production. I mean, as DMRL itself, we started undergoing this transition maybe 15 years ago, because until then we were also very much like an academic institution. We'll develop the product, rather we'll develop the process and say this works. In the case of steel, that worked at 50 kg scale, right? But when you want to go and produce something for the Indian Navy to build those big, big vessels, you need plates that are at least 7-8 meters long, which are 2 meters wide, and each of them, those smaller plates, weighed something like 3 tons, 4 tons, 5 tons. Now, how the hell are you going to do that? Right? So, you'll have to start looking at scale-up issues, and very consciously we are looking at can we link and leverage these two. Right? So, the next 2 things, why this seems too far away, is because R&D and industry, they want actually different things. In R&D, it's the initial phase, it's the excitement phase. This is what stimulates most people in R&D institutions and faculty and students. You want to develop new things, but once you have developed a new thing, you want to go ahead and do something else, right? But in industry, you have to produce the same thing over and over again for a period of time. For example, for the naval steel, for the aircraft carrier, it was produced over a period of 10 years to supply to the same single ship. That means you have to maintain the quality over a period of 10 years. What you made 10 years ago and today should match. So that means it needs for enormous documentation, enormous discipline, and stabilization of the process to be able to do that. Because without that, you cannot guarantee properties, and the more extreme and the more hostile the environment is, the more challenging and demanding it will be on your quality. Okay? So fundamentally, again, I will not go into this. So scalability, you can approach it multiple ways, but you need to establish manufacturing technology as well. So if you don't have a manufacturing technology, you don't have a product. Okay? So now this is just that steel that we made. This is the steel with which the aircraft carrier is built. Okay? It's partial as so this is the entire steel making process. I will not again go through this. The point here to note is that you can process the same steel differently to get very different properties, right? So if you look at this here, you look at the impact on, this is the thickness of the plate, whether it is 13 millimeters or 38 millimeters. Of course, today we can do much better. This is a slightly older data, but it illustrates the concept well. To achieve similar strengths, you look at it in that thickness, it is now practically brittle at room temperature, okay? But same composition, you do controlled rolling, what's called as controlled rolling, and get grain refinement. There is still a decrease, but it is much, much better than this. That means for all practical purposes, this is still ductile, very much at room temperature, okay? So again, this is the theory and principles of rolling, which I will not get into, how we can do. So all this work we did in our lab. That's what I wanted to tell you. You don't have to understand the details, but we looked at where we should do rough rolling, where we should do finish rolling, how we can do, and more importantly, we had to develop processing schedules that are amenable to facilities available in the Indian industry at that point of time, okay? So ultimately, we initially started with an ingot route. So because you have to supply so many tons, like I said, that ship alone took 22,000 tons. So you have to establish a supply chain. You cannot do it once and leave it, okay? So we did a lot of experiments, lab scale experiments, to feed inputs to the manufacturing industry. Then we did continuous casting route to make it more cost effective and to be able to make in greater volumes. And finally, when we did all of that, so many people, agencies, like I said, it will all be a multi-institutional effort. Then finally, all of these ships have been made with that steel. Okay? So like I said, more than 120,000 tons have been supplied of this, and more than 37 warships have been built with Indian steel. And to think that in the year 2000, not even 1 kg steel was being made in the country for this application. Okay? So today we are almost entirely self-sufficient with the steels. So this is again more a scientific work, because that water quenching facility was not there. This again to illustrate quickly to the students that how you can use basic and applied research to address a technology problem. Remember that water quenching facility was not there. Only a 8 meter by 2 meter tank was there. So the idea was, can we develop grades that can be normalized, that can meet properties in normalized condition and not need heat treatment? Again, because many students might not have gone through this, I will not go through this in detail. But the whole idea was, once you understand the physical metallurgy, you can play with the process schedules and then try to develop the understanding. That is what this is about. So I will not talk about the science, but I'll just tell you what. So we took steels with different vanadium content and titanium content. So all of you should just remember that. If you don't know, I'll give it as a fact, that it is the vanadium carbonitrates which go into solution and reprecipitate at temperatures below 1000 degrees. So essentially you're looking at what temperatures you can process, see what is amenable to that. And you can see that the impact toughness in the bottom table is in single digits. Whereas we want 78 joules at minus 60. These are 4, 5 and so on. Right? So how do we control it? By doing a normalizing treatment. And now while all the impact energies are very, very good, strength is met consistently only by one of those 4 steels. So the whole idea was why that is the case. Okay. So this is a multi-pronged approach. One problem using different tools to look at what will happen. So we again used thermocalc. We then found out what is the carbide, what could be there and so on and so forth. Then again multi-scale microstructural characterization, which I showed in the beginning. Right. So then we can tell that, for example, in one of the grades, there was this very big particles, which were essentially oxide titanium containing inclusions, whereas you needed these fine particles to be able to form, to give you the strength levels. We use different strength models then to show that why you are not meeting that in the titanium containing, but why you are able to meet it in the steel without titanium, even though there is always a decrease in both cases from as rolled to normalized. The reason is these fine particles. And even in TEM, we were not able to find the composition of this, even though thermocalc showed us what it was. And that is where this atom probe work was, which I showed you as an animation earlier. This is again the amount of vanadium, and you can see vanadium and carbon of course all over the place. And we were eventually able to show that the particles were essentially carbonitrates, niobium plus vanadium and nitrogen plus carbon. If you look at those numbers, they're more or less similar. In fact, it is essentially niobium nitride with a little bit of carbon and vanadium mixed into it. Sorry, it is a vanadium nitride. So this again heat transfer simulations, and how we can translate lab parameters to industry. A very simple simulation that we did using some software, COMSOL, looking at products of different dimensions. And surprisingly, all we did was to take this and put it in an infinite medium of water, okay, infinite reservoir of water with infinite heat extraction capacity at the interface. You can do all those kinds of studies. And this just gives you clues as to how heat transfer happens. For example, you just concentrate on this last one. Every one of these is dunked into that water with infinite heat extracting capacity when its temperature is 900 degrees into room temperature water about 25 degrees, okay. You can see that, and this is log scale, that for a thin plate and so on, or a thin lap plate, it reaches from that, even the center of that plate, okay, reaches the thin plate center is somewhere here. In less than 10 minutes, it reaches, okay. Whereas when it becomes a block, because in a block you have 3D heat transfer, not one-dimensional heat transfer as in a plate. See, the center of that block does not even know for 100 minutes that it is sitting inside water. Right? These are the insights that you get, whereas intuitively you will never figure this out. You have taken it and put it into water. The surface itself takes so long because of the thermal mass. That is that. But that is starting to move in about 3 minutes. That's why you imagine this is log scale, right? But the center of that block for 100 minutes does not know it is sitting in water. Right? So we use things like this to design heat treatment schedules and what needs to be done. So this is again tempering stuff. This is again work of my undergraduate and MTech students who looked at this. So tempering response, again these are details. I think I will not talk about all of this. Essentially you are able to give industry a working envelope within which they will have to heat treat to achieve the properties that you want. Okay. Again, if anybody is interested, we can go through this in detail. This is another very important thing because we are playing with composition, right? Now this is the same steel. The allowed range of composition, if you happen to intentionally increase concentration of 2-3 elements and at the higher level and keep 2-3 those same elements at the lower level, you can see that this is incidentally a tempering, what is called as a tempering parameter T log T. This would be in Kelvin and seconds. So this is just how you can unify, because again diffusion control processes, so there is always logarithm of time and linear in temperature. You have this A exponential something by 1 over kT kind of a behavior. You will see that this composition is remarkably, that means it is engineered that way, that for wide changes, okay, all these points are either 3 different temperatures, 600, 625, 650 based on those symbols, and timing going from 25 minutes, 50 minutes, 200 minutes, 500 minutes. That's what these are. Okay. So you're having 12 different data points. You will see that, and this is the allowed range, that this low alloy or minor alloy, it's able to meet the properties over a whole range of tempering temperatures and times, whereas this one is able to meet only in the last 2. It is not able to meet, this fails in 10 out of 12. So this kind of information we can give to industry by doing lab scale work. Like I said, this work was done by my BTech project students and an MTech student. So for the steels, to summarize, it's basically that, like I said, from 100% import dependence 25 years ago, today we have all the materials there. So I'll have used another 3-4 slides. It's a so-called valley of death. Okay, you want to take from this proof of concept to application, many things will fail, and you'll see that many of these are outside the technical domain. So that means we still have to be aware of all of this to be able to finally get to the product. This is one reason why people in academia, students especially, do not see that other side, because no matter, many times your research is very good, you get good results, but still it has to go over all these other parameters before it eventually finds application. So one of the ways to make it is to go through it quickly. So just last 3-4 slides is that we look at something like the integrated computational materials engineering, where the goal is to develop new materials in half the time at half the cost or less. Okay. So this is again a big progression that has happened. I've kept that only up to 2013. There's a new thing in 2023 as well. I did not put that in. Fundamentally, this was a materials genome initiative like biogenome. You start looking at, and now AI in the last 4 or 5 years, that word has caught on, but it needs lots and lots of data, right? So you'll have to collect that data, and you can see here that it is computational tools, digital data, and experimental tools. Originally it was this, then those two came, now it is that as well, and you can then look at all of this. And so why ICME? Because earlier our materials development was something like this, very, very linear. You go from discovery, development. So this is what, you see, design, discovery, development, deployment, okay? I did not talk about this, which is very, very important, things like certification and manufacturing base and all that. So, whereas the ICME kind of approaches can make it lot more non-linear and also have a very high slope so that you can make new materials in a much shorter period of time. Of course, each one of these segments should talk to each other, okay? Again, what we need for that, but basically can we realize a digital twin, what is missing and so on and so forth. But essentially, we are now looking at going ahead. We know the conventional route. We want this ICME plus AI plus ML to do, and we need to develop such kind of an ecosystem. Like I said, we look at this. We are now consciously doing this to bring in these approaches, to bring in advanced manufacturing in what we do. And like I already said, we collaborate with academia and industry. There's a much, much greater chance. Right now, DRDO is running, I think, close to 350 odd projects in academia worth more than 1,000 crores. Okay, and we hope to strengthen this in the future. We want to bring in startups, small companies, people with entrepreneurial spirit. But at the end of the day, we need to solve problems of human society. And besides, see, obviously, if you look at the current scenario, national security is very, very important, right? See, some countries taking your oil tanker off, taking it. They're going and taking a president of the country out. Yeah, so you need to be able to be strong and defend your nation. And as we go forward, you also have to address the natural challenges, as it is global warming, these calamities are there, all that. So, important thing for students, I would not say advice is too big a word, is that focus on building your skill set, your competence, your knowledge, and you have to be agile, right? You have to be able to learn new things, maybe unlearn old things. Just in the morning we were discussing with the faculty, the earlier time scales were very large. It gave you 20, 30 years to adapt. But today you will hardly have 1, 2, 3 years to adapt. And the job market is evolving very, very rapidly. So like I started in the beginning, there's a lot of work to do in core engineering disciplines, and it's no more this is materials, this is metallurgy, this is civil, this is mechanical. You have to put all of those together. Civil engineering, you want to build earthquake resistant structures, you build materials which are naturally energy absorbing, right? You can bring in sensors from electronics, have things that will tell you how much the displacement is going to be, what's going to happen, early warning systems. Ultimately, going forward, all this is what is required. So I think with this, I thank you all for a very patient listening. And sorry that video didn't play. Thank you. So again, sorry, many people may not know, but that Nataraja statue which stands in front of the DMRL building, and we work on investment casting, which is used for nickel-based superalloys for turbine applications. So what was made for the Chola bronze idols, the same technique is used to make very, very sophisticated engineering components. And it is just called precision investment casting. Thank you.
For your insightful lecture, we now invite questions from the audience.
Nobody has the energy to ask questions.
Do you have for your materials processing maps like Richraj maps or what Vaigarika Prasad and Shashidhar did? Do you have that for these materials?
Yes, processing maps are being developed. Like I said, I did not touch upon that because in these kind of steels, more or less, we do have a much wider window. But or nickel-based alloys and things like that. We always do processing maps and deformation maps, looking at temperature, strain rate, and then the efficiency where you can process, because otherwise they'll simply crack. We do those. Yeah.
But you have it.
Yeah. My only thing is today, I think your software, your equipment has improved, that we are able to generate those. Sir, those days, it was one PhD if they did it for one alloy. Today, we are able to do much of that in maybe 3 to 6 months. Yeah, volumes, yes. And internationally, 400 people were involved, I think. 400 people were involved internationally to generate those originally. But for these modern alloys, again, sir, whatever we do now, like they said, we are only standing on the shoulders of giants and taking it forward, sir. So, but it is still very important. Without that, how do you do? Because, and especially the newer alloys, where the processing window is much smaller, increasingly you are working with more BCC alloys, where the number of slip systems is less. So, alloys like niobium alloys, molybdenum alloys, they'll simply crack. So, yes, sir, all that is there. Yeah.
Sorry, sir. Do you work on electroslag refining, electroslag welding and such processes?
You are asking us, do we work?
Yeah.
No, we don't do. We used to do. Professor Ballal was talking about Dr. Balidad and other people who are there. So, but yes, but today it is an established process, so we don't work on it anymore.
Okay.
I mean, like I said, we are an institution where normally we do only when others won't do it, can't do it, or will not, or don't have the will to do it.
No, but how exactly that underwater vehicles, how exactly they are welded?
E-beam.
Electron beam welding. But such a thick material?
No, again, that didn't play properly. Yes, it is a fairly thick titanium shell. Okay. Yes, they have developed techniques where within 2 passes you can do about 70 millimeters. Sir, no, don't we take help, sir? We have to work together. See, none of that we do in the lab, right? Yeah. So, a lot of that was done in Midani only. See, what happens is we develop at lab scale the titanium alloys. Which one? Yeah, that comes because it's a DMRL project. We only developed it. Midani, sir, that one Midani doesn't do it. Midani, for that project, the aircraft carrier that I showed, Midani is too small. See, today we are making plates that are 26 tons. Each plate weighs 26 tons. No, they don't, because you need an integrated steel plant. So we are working with Rourkela steel plant. We are working with 4 different plants of SAIL. We are working with what was earlier SR Steel, that is AMNS. We are working with JSPL. Today we also make forgings. Our single forging is 24 tons. One forging weighs 24 tons from a 84-ton ingot. So India today, I mean the last 15 years, the kind of capability we have built in the country is enormous. So that, sir, that's what, sir, that was done in L&T only. Yeah, they did that more as a demo, yes, to keep 3 heats in the ladle and cast a slab which eventually yielded 196 tons. But that was more a demo. Routinely they do 100 tons. Yeah. And that's what I said, sir. It is all have to do with industry only. You cannot do on your, it's no more like I did. It's like we as a country have to get the product delivered. Yeah.
Yeah, I have 2 questions. The first question is on the material tetrahedron. I happened to attend one lecture where they have said that now there is another dimension to it where you have material discovery. So, for example, Microsoft has come out with a large number of materials, and they are all thermodynamically feasible, but unfortunately there are no techniques by which you can synthesize those materials. So, I mean, whether DMRL is working on...
We are looking at that. In fact, I did mention that that central characterization, you can put many more things there.
Right.
One of it is this. In fact, there's a huge debate. There are people evenly divided on both sides of the debate. What do you actually mean by discovery? Because, see, all of us who know, I mean, metallurgical thermodynamics was talked about, right? See, if you say, you take a 5-component alloy, long back with it, you take a 5-component alloy, and you say every 0.1% is a significant change, then within the 5-component system, you are having a huge number, like about 2 million, if I remember correct, 2 million kinds of compositions, even if you restrict that range.
Right.
Now you open it up to 9, 11, many of these, it's like the nickel-based alloys, they have 13 elements, and an alloy like CMSX4, you have to report 53 elements in its composition certificate. 43 of which about 15 are poisonous. 53 elements you have to report for you to be able to accept it. So today if you make it, we do not have enough labs in the country who can analyze those 53 elements. There are only 4 labs in the country that can do it, including DMRL. So yes, theoretically yes, many things can be done, but what is practically feasible? Definitely those are good methodologies for us to go ahead. But we should not say Microsoft has discovered 10 million materials.
No, they have used some AI techniques or
True.
and DFT. And,
so it's discovered in the sense that it is plausible that those can be made, right?
Yes,
True. That is why I was very careful to use engineered and engineering. So we don't dabble in that world. But there could be useful solutions there. In fact, we ourselves have done, I did not talk about it, 170,000 compositions were screened to give only 5 compositions. In particular, nickel-based alloys, which are used for powder metallurgy discs. And we made them in the lab. All alloys met property first time right. 170,000 compositions were investigated over a 8-month time frame, entirely digitally. We use thermocalc and Dictra only, use some certain screening constraints, right? Obviously, you can make at best 20 or 30 alloys in a year in the lab. So imagine making or exploring 170,000. So yes, so we do that.
And the second question is on the heat transfer simulations, where you have shown the temperature time. Because they are simulated or they are, experimentally measured?
No, they are simulated.
Simulated, okay. That means you said you are giving the boundary conditions.
Yes, it's essentially a multi-physics model.
But in which case, it's an ideal condition because H has to be infinity.
Absolutely. What I'm saying is, in an ideal condition, it can't see that it is quenched in 100 minutes. Imagine in a real condition. See, good you raised that point. So for the students, these days, because finding the exact answer is very difficult. So you do what's called as a bounds analysis, right? So whether it's the lower bound or the upper bound, you just have to be conscious what it is. That means in real life, we know it's going to be much, much more than 100 minutes. Yes, so that's what we did.
Okay. Thank you.
Thank you.
This is Matsya 6000, a deep water manned submersible to take 3 human personnel to the hadal depths of the ocean. This manned submersible is being developed by National Institute of Ocean Technology, NIOT, under the Deep Ocean Mission of Ministry of Earth Sciences, Government of India. Matsya 6000 is an underwater vehicle capable of underwater travel to a depth of 6,000 meters. The underwater travel duration can be for 12 hours in normal conditions and 96 hours in abnormal situations. Matsya 6000, which is 10 meters in length and 3 meters width, 5 meters in height, weighs 28 tons in air. It floats in seawater with a positive buoyancy. The Matsya 6000 design has a 6,000 meter depth rated watertight pressure hull or personnel sphere of 2.1 meters in diameter, which can accommodate 3 personnel. It has 3 viewports to allow personnel inside to view the subsea environment with the help of illumination provided by underwater lights. With a forward speed of 3 knots in water, achievable using underwater thrusters, it can do subsea research, survey sampling, and intervention. The ascent and descent motion of the vehicle will be given by the ballast and trim system, which is energy efficient. Matsya 6000 will be powered by lithium polymer batteries with an energy budget of 100 kilowatt hours. Redundant control architecture and fail-safe emergency and salvage systems will be the key features of Matsya 6000 system. An A-frame based launching and retrieval with support systems in operations research vessel Sagar Nidhi are envisioned for the Matsya 6000 system. India will be the 6th country to develop a deep water research submersible along with the United States of America, Russia, France, Japan and China. With a project cost of 300 crores, Matsya 6000 is developed in India by NIOT and some of the subsystems realized through global partners. Within the next 3 to 4 years' time, Matsya 6000 will be launched into operation. pre-dive check of manned submersible will be carried out on board the ship, along with one pilot and 2 crew members who embark the manned submersible on the ship deck. Hatch cover will be closed on board and ready for launching. The life support system will be switched on and the diving time count will be started. Launching the vehicle into the water using an AFT A-frame and checking for piloting functions in surface floating conditions. Vehicle will be floating with sufficient freeboard. After carrying out a functionality check of the vehicle in surface floating condition, divers shall release the lifting hook to disengage the submersible and open the manual vent valve for the descent. Pilot will open the vent valves and main ballast tanks are flooded with water. The vehicle will start descending. During the descent, communication between the submersible and the ship, including navigation parameters, vehicle system health, and human life support systems data, shall be through the acoustic communication link. During the descent operation, the velocity of descent shall be controlled predominantly using service drop weights and finer adjustments using a variable ballast system and the thrusters. Using a combination of thrusters and ballast system, maneuvering shall be done at seafloor for the intended purpose like survey, scanning, sample collection, etc. Depending on the sample weight collected during the survey at the bottom, drop weights can be dropped to compensate for the sample weight addition. Keeping the low water level in the variable ballast tanks at the beginning of the ascent helps in taking in water or gaining weight and reducing the submersible ascent velocity as it approaches the sea surface. Before surfacing, at 100 meters water depth, manned submersible shall be stopped to get clearance from the mothership. This is achieved by filling the VBT during the ascending phase and using thrusters if needed. As the submersible surfaces, using the compressed air blowdown operation, water shall be pushed out of the main ballast tanks to ensure sufficient freeboard. Divers shall board the submersible, hook the submersible with the launching system, the A-frame, and recover the submersible on board the mothership. And the Matsya 6000 is taken on board the ship safely.
This is thanks to my colleague Dr. Vedachalam at NIOT. Of course, this is also to show that there are very complex non-defense projects that are going on. I mean, like I said, this is taken up as a national mission. It's directly monitored by the Principal Scientific Advisor to the Government of India. And Ministry of Earth Sciences is steering it, but many, many departments and ministries are helping them with various aspects of that entire program. Thank you.
Thank you, sir, for addressing the queries patiently and looking forward to reading more about Matsya 6000. As a token of appreciation, I would now like to request our Deputy Director, Professor Subhash Yaragal, to present a memento to our Chief Guest and Speaker, Dr. R. Balamuralikrishnan. May I now request Dr. Selvakumar Murugesan to propose a vote of thanks.
Yeah, very good evening to all. Respected Deputy Director Professor Subhash Yaragal, our Chief Guest Dr. Balamuralikrishnan, and our HOD of MME, and former professor as well as present faculty members, and my dear colleague, friends, students. And it's my privilege to stand before you all to say a word of thanks and thank who have made all these 35th Professor T. Ramchandran lecture possible. Well, first of all, I thank Dr. Balamuralikrishnan for accepting to come over here all the way from Hyderabad, despite his busy schedule. And he has given such a wonderful talk and sharing his whole research experience. And we are truly enjoyed and motivated by your words, sir. Thank you so much. I also thank Professor Subhash Yaragal for presiding over this function, today program, and guiding us with his various thoughts. Thank you, sir. And the gratitude goes to many people. First of all, the HOD of our department, Professor Kumkum Banerjee, and then Professor Jagannath Nayak, Professor Uday Bhatt, Professor Narayan Prabhu, Dr. Rajashekaran, Dr. Sumant, and Shashi Bhushan Arya, for their valuable contribution in various aspects. I also appreciate the efforts of our organizing team, which is headed by Karthik, who is a PhD student of our department, and then various teams, including the MCs and then the security team as well. So as a token of appreciation, and we would like to give a small gift to our MCs team. So now I would like to call Dr. Leepak Kumar Sago to give a small gift to our MCs as well as the invocation team. MCs Anaswara and Aranidya. So I also invite the invocation team, Harsha and Anaka, to the stage. Well, once again, on behalf of Metallurgical and Materials Engineering Department, I thank each one of you for being here and making this even more successful. Thank you so much.
Now I request everyone to rise for National Anthem. Now I request everyone to join for a group photo.